Hello and welcome to York Observatory TeleTube, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. I'll be one of your hosts this evening. My name is Dorsa, and I'm joined by Maheen, Nakul, and Sergiy, broadcasting live from Alani Carswell Observatory, located at York University in Toronto, Ontario, Canada. York YouTube broadcasts every Wednesday night at 7:30 p.m. local time. And for any questions or comments you have for our past shows, or if you have suggestions for any future topics, please send us an email at observe@yorku.ca. You can always connect with us on Twitter or Instagram with the handle @YorkObservatory and Facebook at Alani Carswell Ubs. Good evening, everyone. I'm Dorsa, and tonight we've got a very special guest, Dr. Adam Frank, coming from the University of Rochester, who's going to talk about the search for alien life in the universe. But before we go on with the presentation, we'd like to mention that the observatory at York campus is in Toronto, and we would like to welcome you all to our show and to acknowledge the traditional land that our telescope is on. The observatory acknowledges its presence on the traditional territory of many Indigenous nations. The area known as Toronto has been caretaken by the Anishinaabe Nation, the Haudenosaunee Confederacy, and the Huron-Wendat and the Métis. It is now home to many Indigenous peoples. We acknowledge the current treaty holders, the Mississaugas of the Credit Face Nation. Our stargazing and astronomical efforts join the long history and current practices of astronomy for this land. The observatory looks forward to continuing to learn and revitalizing our knowledge in this area. I'm now giving it away to my colleague, Maheen. Take it away.
Thank you, Dorsa. Welcome, everyone. Before we get started with our main show, we want to give you a little update on what you can see this coming week. Moon is currently in its first quarter phase with an illumination of 45.34%. Yesterday, we had the nearly half-illuminated moon positioned several fingers worth to the right of the main belt asteroid designated as 4 Vesta. Binoculars could be used to get a shared view of the moon with Vesta. Saturn was also visible to their lower right nearby during early evening. For anyone who missed this, don't worry. Tonight, for the second time this November, the moon will complete the first quarter of its journey around Earth. Moon will be shining in Aquarius below the bright planets of Jupiter and Saturn. With the telescope, you can look at asteroid Juno, sitting less than a lunar diameter to the moon's lower left of the celestial south. For the moon, evenings surrounding the first quarter are best ones to see the lunar terrain when it is dramatically lit by low-angle sunlight. Another exciting event tonight is Mars being closest to Earth, since it is a week before it will reach opposition on December 8th. Using a telescope for this will reveal the greatest amount of surface detail. The planet will shine high in the southeastern sky between the horns of Taurus. Mars will continue to brighten in the sky until opposition, which provides a good viewing opportunity this week when the weather permits. Jupiter is also currently a good observing target. Position highest and appearing sharpest mid-evening. With Uranus reaching its opposition on November 9th, it is currently an all-night target, especially during late evenings when it will be highest and appear clearest in binoculars and backyard telescopes. If you're interested in observing star clusters, one of the clusters visible tonight includes Pleiades. Pleiades, also known as the Seven Stars, is an open star cluster which contains middle-aged hot B-type stars in the northwest of the constellation Taurus. Locating the famous constellation Orion can be a good way to find the cluster. Draw a line using the 3 stars in Orion's belt and then follow it upwards past his bow. Now that we have gone over observing opportunities in the sky in the next couple of days, I wish you all happy observing, and will hand it over to Sergiy to introduce our guest speaker, Dr. Adam Frank, for tonight.
Thank you, Maheen. Now on to tonight's esteemed guest, Dr. Adam Frank. According to his website, Dr. Adam Frank is a professor of astrophysics at the University of Rochester, where his primary interests are that of stars, namely how they are formed and how they die. He is a leading expert on especially the final stages of evolution for stars. Besides that, Dr. Adam Frank is the head of a computational research group at the University of Rochester, which developed advanced supercomputer tools to study and simulate the formation and death of stars. In addition, he also has a second career as a popular writer and speaker on the subject of the beauty and power of science in its proper context and culture. So great is his love of science, he described himself as as the evangelist of science. Since Dr. Adam Frank was 5 years old, he fell in love with astronomy, which eventually evolved into a love of all of science. This love is primarily thanks to his father, whose pulp science fiction magazines inspired Dr. Adam Frank's imagination of alien worlds of possibilities, and through his father's explanation of sound waves and electric currents, a thunderous world became filled not with fear, but marvel. He also created the free Coursera course confronting the big questions highlights of modern astronomy. He co-founded Big Things 13.8 blog, as well as a regular on-air commentator for All Things Considered. He wrote 3 books: The Constant Fire Beyond the Religion and Science Debates, About Time, Cosmology, and Culture at the Twilight of the Big Bang, and Light of the Stars, Alien Worlds, and the Fate of the Earth. He also wrote the textbook Astronomy at Play in the Cosmos. Also, his upcoming book called The Little Book of Aliens will come out next fall, so we are super excited about that. Make sure to check it out, folks. This book relates to tonight's topics, where Dr. Adam Frank will be focusing on the search of alien life in the universe. So please take it away, Dr. Adam Frank.
Thank you. It's a pleasure to have a chance to talk with you guys today. All right, so I'm going to share screen here. I need to stop the other sharing, so I'm going to do that, and I will start here. Excuse me. Okay, so what I'm going to be doing today is giving you a little talk about aliens, technosignatures, biosignatures, and I'll briefly talk about how this connects to things that happen on Earth. Okay, so the thing about the thing about SETI or the search for life is that it's such an old question that it's really worthwhile pursuing the history a little bit of it to understand where any of this, the context in which any of this occurred. So we're going to do a little history, that what I call the heroic age of SETI, and then we're going to talk about what's changed now in terms of what I call the 3 revolutions in astrobiology, and then we'll talk about biosignatures, and then we'll talk about technosignatures. So that's kind of our little outline for the day, or for the evening. So we're going to start off with Enrico Fermi and his famous paradox, or his famous question. And this goes back to, this is really the first time that anybody had, hold on a second, this one, yeah. The first time that anybody had really formulated a question. People have been thinking and arguing about life in the universe for a long time, but this was the first time that anybody formed a question that could eventually be investigated scientifically, as opposed to just arguing with each other. And so there was, he was at the Los Alamos National Laboratories. This is 1950, and he and some colleagues are walking towards lunch, and they start arguing, or they start talking about UFOs, because UFOs were already a thing, and there was this cartoon in the New Yorker that one of the scientists brought up. The conversation got to UFOs and how, could UFOs actually travel in between, interstellar, and what that would require, interstellar propulsion. And so, as typical scientists, they bounced around a bunch of ideas, and then they forgot about it. The conversation moved on. And then about an hour later, over lunch, Enrico Fermi asked this question: but where are they? And what had happened is Fermi had already seen into the heart of the problem, where he recognized that if intelligent life were common, then you would expect that, or if intelligent life were common, then what he saw immediately was that even a single star-faring species could, in a time that's short compared to the age of the galaxy, make it from one end of the universe to the other. So as we'll see, this is what becomes the Fermi paradox. By the end of the 1950s, Frank Drake, who's pictured here as a young man, was carried out the first search for signals from an extraterrestrial civilization. And so what he does is he uses this new telescope that's just been built at the Greenbank Radio Observatory, and he calls this project Ozma. Ozma is the princess in the Oz stories, which he was a big fan of. Excuse me. And so he does this search. It's the first time anybody in the entire history of humanity, and people have been arguing about alien life for 2,500 years. You can see the Greeks actually beating each beating each other up over it. He carries out the first search, and he doesn't find anything, but it certainly captures the public imagination, and it launches what we call SETI, the search for extraterrestrial intelligence. So Drake does this, and then he spends the next year looking over his back, thinking like, who's laughing at me behind my back, right? And instead of finding out that people are laughing at him, he actually gets a call from the government asking him to lead a meeting on interstellar communication, because it turned out the government was actually interested in this. So he puts together a meeting with just, these people, Carl Sagan, Otto Struve, et cetera. So it's not a huge meeting, but this is the first time anybody has ever gotten together as scientists to sort of ask themselves, well, is interstellar communications possible? Is there life in the universe? And the most important result of this is actually the agenda that Drake puts together for the meeting, because it was the first time anybody had ever discussed this. So what was there actually to discuss? So he puts together this formula, which is really an agenda for the meeting, because what they did is this formula is N here is the number of interstellar civilizations number of civilizations in the Milky Way galaxy that we could communicate with. And so what he did was he said, like, well, we can break that. If we want to know what that number is, we can break this into a bunch of sub-problems, which are each identified here as a factor in this equation. Let me just go through this. R here is the number of stars in the universe, or in the galaxy, excuse me. Actually, it's the number of stars forming per year, which is just another way of saying the same thing. F sub P is the fraction of those stars that have planets. N sub E is the number of those planets that are in the right place to form life, meaning that you could get liquid water on their surface. F sub L is the fraction of those planets that have liquid water on their surface that actually go on to form life. F sub I is the fraction of that life that goes on to form intelligence. F sub T is the fraction of those intelligent species that actually produce technological civilizations. And L is how long those civilizations last. And so if you knew all of these numbers and multiplied them together, you would get the total number of civilizations in the galaxy. And of course, if N is very large, then there's a lot of civilizations to find. And if N is 0, there's nobody else out there. And so this, what was important about the Drake equation is that it broke the problem up. You could just spend your time studying how many stars there were in the galaxy. You could spend your time figuring out how often planets occur. You could spend your time studying whether or not those planets are in the right place, et cetera, et cetera. So this really, the Drake equation was really important because it helped astrobiology, the study of life in the universe, it gave it a research program. Another important idea was this idea of Dyson spheres. If it was 1960, Freeman Dyson proposed that if an intelligent civilization, as civilizations become more and more advanced, they're going to need more and more energy. And what's the best energy source for a civilization? It's their star. And so a really advanced civilization would be able to cover their star in a giant sphere of solar collectors and basically get all the energy that the star was putting out. And we're going to see this, we're going to come back to this idea. So Dyson spheres, as they have been called, are an idea that has just really lasted. There's also the idea, same time around 1964, the Russians were very interested in SETI. This guy Andrei Kardashev, comes up with his scale. He was also thinking about civilizations and how they change over time and as they advance. And he came up with these 3 types of civilizations based on how much energy they use. And a type 1 civilization would be able to use all the power available to the home planet. A type 2 would be able to use all the power available from the star. That would be like a Dyson sphere. And a type 3 would be able to use all the power available from all 400 billion stars in a galaxy. And again, this is an idea that just the Kardashev scale, if you go out and you watch any YouTube videos about life in the universe, you're going to see people talking about the Kardashev scale, and you're going to see people talking about the Dyson spheres, and you're going to see people talking about the Drake equations. This is all sort of foundational stuff in astrobiology. Now let's just talk a little bit more about Fermi's paradox. So really the Fermi's question, it takes about another 15, 20 years before anybody really nails exactly what the scientific question was. And it was Hart in 1975 who realized that really worked out what Fermi had seen just by thinking about it. That's how bright Fermi was, what a genius he was. What Hart showed was that even a single civilization, if it just traveling at, say, 1/10 of the speed of light, started sending out colony ships or settlement ships, that it could hop from one star to the other and get settle the entire solar system in about 600,000 years, which sounds like a long time, but actually the galaxy is 10 billion years old. So the fact that there were no so that it would in a blink of an eye, the whole galaxy should be able to be a single civilization could settle the entire galaxy. And so for Hart, this was the fact that there are no aliens on the, there's no settlement here already, that the aliens haven't landed on White House lawn and announced themselves. For him, he called that fact A, and the fact that there were no settlers here now meant there were no aliens anywhere, that we are the only civilization in the galaxy. Now, other people have pushed back against this, but the paradox, this idea of the Fermi's paradox, that there's so many stars in the sky, and if intelligent or if life is common, then why don't we see aliens right now? That paradox is going to come back to us, and we're going to see a lot of people argue about it. And there were rebuttals against Hart, like Carl Sagan thought that that the settlement wave, if you imagine these the aliens sending out ships going from planet to planet, that eventually it would slow down or stop because of resource issues. So not like most people actually pushed back against Hart, but this Fermi paradox it's been around out there quite a long time. Now, we have to distinguish between the direct and indirect version of the Fermi's paradox, right? So Fermi's fact A, this idea that why is there no one here now? That was what we could call the direct version of the paradox. So that's a hard one to get around, right? But there's also what people have said. There's also people will talk about the Fermi paradox in an indirect way. They would say oh, look, we've been looking, like what Frank Drake did. We've been looking for aliens for a long time, and we haven't found any. So why is it, so it must mean that there's no aliens out there. And this led some people to come up with the idea of a great silence, that we've searched the night sky and we have found nothing, and therefore there are no aliens out there. We're the only ones, and we face the great silence. And because of this, people have also come up with the idea of the great filter. There must be something, if this is true, there must be something which is keeping civilizations from evolving. Maybe the great filter could be something that it may be very hard to form intelligence, and human beings just got lucky. We're the only ones in the whole galaxy. It could be that it's later in evolution. Maybe everybody wipes themselves out via nuclear war or some other cataclysm that's 1,000 years in our future or so. Now, the thing I want to point out, because we're going to come back to this, is I'm going to tell you right now, this second version, the indirect version of the Fermi paradox, just doesn't exist for reasons I'm going to tell you about. There is no indirect Fermi paradox. It's a mistake because people don't really understand how much SETI has been done, but we'll come back to that. Okay. All right, we don't need to cover this. I do want to note that classic SETI was really based on the idea of radio, of looking for beacons for reasons I won't go into. It was logical, if you're using radio, to look for, basically the only thing you could look for was some alien building a giant lighthouse and sending all of the energy and transmitting all of their energy in a beam, as if they were trying to let somebody like us, they're beaming it at a message at us, and they're trying to let us know that they exist. I think there's a lot of problems with this, it's not a lot of problems, but there's some issues with this. And this was, at the time, this was the best anybody could do. But for me, it's a little bit limiting. And as we'll see now that this is with the new age of biosignatures, things have really changed. So this idea of purposeful beacons, which is what most of classic SETI was about, radio SETI was about, you need to assume that somebody's trying to send you a message. Now, what happens in the history of SETI is that, NASA for a long time was very interested in SETI and provided funding for SETI. But then around 1978, we entered the dark ages, and it was all because of politics. So, for example, in 1978, William Proxmire, who was a senator, who loved to try and find things that he thought were wasting taxpayers' money, lands on SETI and goes after SETI and says he awards it his Golden Fleece Award and says, oh, it's a waste of time. Why are taxpayers, looking for little green men? And so it actually puts legislation that says NASA cannot fund SETI. And so it kills SETI funding. And then in 1990s, NASA tries again to fund SETI, and it once again gets burned. Congressman Conte, famously said, "Why spend millions on SETI when for 75 cents I can buy a tabloid and see pictures of aliens?" So, it was just, and so basically NASA was like, "Wow, we are not going near this again. We just, we got enough other things to deal with. We don't need this political headache." And so basically the funding for SETI dries up. It's not like there was ever that much funding to begin with, but now like NASA is not funding SETI. Except maybe little teeny tiny amounts on the edges. SETI was running on fumes, and it seemed like astrobiology, the study of life in the universe, was just not really, there wasn't going to be a whole lot of activity in it. But then, as I like to say here, nature and science had other plans for us, and that's because of these three great revolutions in astrobiology. Again, astrobiology is the study of life in a planetary, cosmic context. So the first thing that happens is that in 1995, the first exoplanet, the first planet orbiting another star, is discovered. And that is, this is a 2,500-year-old question. Again, you can see the Greeks are arguing about it. In the Aristotle, Democritus had opposite views on this. For 2 millennia, people were wondering whether there were any other planets in the universe other than the ones orbiting the sun. And it was very possible that planets were just very difficult to form. And so they were very, very rare. And so this discovery of the first exoplanet completely changed everything. And within, a few years, we realized that there were lots of planets orbiting the universe. Orbiting stars in the universe. And there were many planets that were in the right place, what's called the habitable zone, the zone of orbits where you could pour liquid water, you could pour a cup of water on the surface and it would just sit there in a puddle. It wouldn't freeze and it wouldn't boil away. So that means, since we think life is water is so important for life, that was a big change. Second revolution was solar system studies. We sent probes to every type of astrophysical object in the solar system, or every type of solar system object. So we visited all the planets. We have been to comets. We've been to asteroids. And that gives us a huge amount of understanding about the evolution of planets. So, now you look at this picture could be like the desert in Tunisia, but it's actually Mars. And what we've learned from having robots rolling around on Mars is that Mars once was a blue world. Right now, Mars is a frozen desert with very little air at all. But at one point, there must have been enough air, thick enough atmosphere that you could have liquid water on the surface, because we have clear evidence that Mars once had a fair amount of water on its surface. So we've learned quite a bit about how planets evolve in their long history from solar system studies. Now, the next revolution, I always like to show this picture and ask a question: which one of these pictures is Earth? So here's 6 planets. Which one of them is Earth? You don't have to answer, but the answer is all of them. So Earth has been many, many planets over the course of its history. And so this is the third revolution. We now understand Earth's deep history. So to go back to this, this is Earth very early on, when it was a magma world, just after it formed. And then after a while, when Earth cooled down, there were no continents. It took a while for the continents to grow. And so we were mostly a water world. And then there have been periods when Earth has been so warm, it's been a jungle world. There's been no ice anywhere or snow anywhere, almost. And then there have been periods when it's all ice and snow, and the snowball phases, when the Earth is almost entirely frozen over. And then here's our beautiful version of the Earth right now. And in the future, here's the horrible Earth that once as the sun heats up and the oceans are boiled away. So from Earth's deep past, we have learned an amazing amount about planets. How from Earth's deep past, we've understand how planets and life evolved together. All of this is going to change our understanding about searching for life in the universe. So one thing you could say is, okay, how did this change anything? How did all these 3 revolutions change anything? Well, remember the Drake equation, right? When Drake came up with this equation, there were only the only term that was known, there's 7 terms here, was this one, the number of stars forming per year in the Milky Way. And thanks to the exoplanet revolution, and thanks to the 3 revolutions of astrobiology, we now know this one and that one. That's pretty good in just 50 years or so to make so much progress. And so we know that every star in the sky, when you go outside tonight and look at a star, go outside and look at a star if you can see it, if it's not cloudy. Every star in the sky has planets, a family of planets. And if you count 5 of them up, one of those stars, one of those 5 is going to have a Earth-like planet in the position to be able to form that we're looking. You could have liquid water. It'll be a planet. 1 in 5 will have a planet in the habitable zone between 1 and 4 and 105, 1 and 5. And there are 400 billion stars in the Milky Way. And that means there's about 100 billion habitable zone planets. And every one of those planets is an experiment that nature is running in the possibilities of life and intelligence and civilizations even. So, quite a bit has changed from this, the exoplanet revolution. And so now let's go on to where we are now, because what the exoplanet revolution and the other revolutions changed in terms of the search for life is that we now know exactly where to look, and we now know exactly what to look for. And I'll tell you what I mean by that. With SETI, you just had to, with traditional SETI, you just had to point your star at your radio telescope at a star and hope for the best. Like maybe there was a planet there, maybe there wasn't, who knew? But now we know where all the planets are. Not only that, we know where the planets that we care about are. We can look exactly at them. And we also know exactly what to look for in terms of, we now understand what kind of signatures life would imprint on the light coming from that planet that we could observe on Earth. So let's talk a little bit about that. So this is the idea of a biosignature, right? If we're looking at a planet that's 50 light years away, we're not going to that planet anytime soon. But we don't have to, because there is a way in which we can search for life just by looking at the planet. And so what we're going to talk about here for a second is the method of finding planets called the transit method. And a transit here, let's look at this picture over here. You see the star, and a transit happens when the planet passes between us and the star. So there's a moment there where the light, a little bit of the light from the star is blotted out by the planet. You can actually see a diminution in the light. And that is what tells you that there's a planet there. But even more important, while the planet is passing in front of the star, some of the light from the star actually passes through the atmosphere, if there is an atmosphere. And as that light passes through the atmosphere, it will be absorbed by chemicals in the atmosphere, and it'll leave a trace in the light. So when you look at, so over here, you see this would be what we call a spectra, where we'd be looking at the brightness of the light from the star as a function of frequency. And if we were looking at during this transit happens, we may see these places where the light has been absorbed. There's less light at specific wavelengths. And this is like this is a fingerprint in the light of certain kinds of chemicals being in the atmosphere of the planet. And what we might see are chemicals that can only be there because of life. That is what we're interested in. So this is what we call a biosignature. You might see methyl chloride or methyl bromide or isoprene or dimethyl sulfide. These are all chemicals that only life produces. It's very hard to imagine that a dead planet could ever produce these kinds of chemicals. So that's what we call a biosignature. And actually, the most important biosignature is probably oxygen and methane. Oxygen in the air we breathe is only there because of life, because of plants and microbes breathing out oxygen. And methane, if all life went away tomorrow, the oxygen and the methane would very quickly react away together. And we'd go back to having a planet that had no oxygen in its atmosphere. So if we ever found a planet that had oxygen absorption lines and methane absorption lines, we'd be pretty certain that came from life. And so here is this is a nice plot. What we're looking at, or figure, we're looking at Earth at 3 different times, and this is a spectra again. And so you look at the Archean Earth, that's about 3 billion years ago, or 3.5 billion years ago. The Proterozoic Earth, and that is on the order of billions of years ago, and then the modern Earth. And you can look at the spectra, and what you see are the lines here. These lines are chemicals that you can identify. So methane, we see in the Archean Earth, we see lots of methane, carbon dioxide, because there was no oxygen in the atmosphere yet. The oxygen didn't happen until life put the oxygen there. And that was about 2.5 billion years ago. So you look later on, and what you see is, if once you get to 1% the level of oxygen, you see a deep absorption line here, a place where like they add that atmosphere that if it was the Earth, if someone was observing the Earth from a distance, you would really be able to tell that there was oxygen. This is actually ozone, oxygen 3. So there would be this deep line here from that was evidence of oxygen in the atmosphere. And in the modern Earth, you've got the ozone line, and you've got lots of oxygen lines all over the place. So, you know, if you were looking at Earth from a distance right now, you could definitely tell that there was life there. Okay, so that's biosignatures. So now there's a lot of work going on about biosignatures, and we are the JWST has the possibility of finding biosignatures. It's, you know, it's at the hairy edge of the ability to do that, but it is possible. And most important, the next generation of telescopes after the JWST, the telescopes that will be built the next 10 years, 20 years, 30 yeers, those ones are they're going to be built specifically to find biosignatures. So, you know, this question, which people have been arguing about for the last 2,000, 3,000 years, we're going to have it answered in the next, or we're going to have data. I don't know what the answer is going to be, but we're going to have relevant data in the next 2 or 3 decades. That's incredible, right? So we are really finally beginning. Now, what about smart life? You know, what about not biosignatures, but technosignatures, signatures of a technological civilization? And so for a long time, as I said, NASA was like, nope, we're not doing this. We don't want to get involved. But the exoplanet revolution really changed that. And in 2018, Congress here in the US, actually, somebody put language into the budget that said, oh, you got to spend $10 million to look for technosignatures. And NASA was like, what? We got to do what? And so suddenly they had to sort of, you know, so they brought a bunch of us together and said, like, well, what should we look for? And so this was really a great moment. There was this meeting in 2018 in Houston, and that the people who were interested in technosignatures were invited to. And it was really a signal that, like, oh, things are changing now. Now that $10 million never showed up, but it didn't matter. Now, you know, because NASA's interested in this question. It was just politically, it wasn't very, you know, they knew they were going to get themselves into trouble if they tried it. But now NASA was saying, or Congress was saying, no, go do it. So this is the new era. And now there's actually, I'm the principal investigator on a team of, that we're looking for technosignatures. And Jason Wright is another member of our team. And this is a big grant proposal. We put in a much bigger grant proposal, which didn't get funded, but the next one probably will, hopefully. And so right now, we've, there's like now I think NASA has like 4 or 5 different grants that are oriented towards technosignatures. So I just want to run through some ideas of technosignatures. Now, again, you're not doing SETI anymore. You're not just like taking a radio telescope and pointing it some random place. You're now going to use like optical telescopes or infrared, and you're going to look right at the planet, at the exoplanet. So let's think about some ways that we might be able to find technosignatures. So remember I talked about Dyson spheres, right? The idea of these, like, these spheres of solar collectors being built around a star. It turns out that even Dyson never meant an actual sphere, because if you tried to actually build a giant sphere, it would be unstable. It would eventually just sort of like tilt away and actually hit the star, which would be very bad. But what he really meant was a swarm of mega structures of giant solar collectors that is like a swarm that was orbiting the star. And this idea actually is also one of the things that kicked off the modern era of technosignatures, because there was this famous case back in 2016 of Biosignatures star. And this was a star where people were they were using the Kepler telescope to look for transits. Remember these little dips that occur when a planet passes in front of a star. But there was this one object that didn't look at all like planets. Instead of a nice smooth dip that, stayed for a while the planet was in front of the star and then the starlight comes back, you had all of these weird, irregularly timed dips back and forth. And nobody knew, this is not expected at all. Nobody knew what this was. And when they wrote the paper up on this, one of the things they said was oh, it could be comets. It could be, clouds of gas. It could be a fractured planet. And it could be alien megastructures, right? Now, the interesting thing about this is this was 20 years ago, that never would have been allowed in the paper. People, the referee would have been like, that's crazy. You can't even say that. But we've got to the point now that we're staring at all these planets that it's possible. And, of course, you're going to need extraordinary evidence to say whether or not that's true. But you're not wrong to include it in your list of possibilities. Now, sadly, or not sadly, depending on how you look at it, it turns out to be clouds of dust. But, you know, it could have been alien megastructures, and we're going to keep looking for the possibility of alien megastructures. Another possibility is that with the next generation of telescopes, we might be able to actually make, by doing tomography, we might be able to actually make maps, crude maps of the surface of these planets, of these exoplanets. And we'll be able to possibly tell whether there's city lights on them. If we look at the night, at the night side, we would actually be able to see artificial illumination on them. So that's pretty exciting. You could see city lights, and that would tell you that there's a civilization there. Likewise, you might also be able to see the spectral imprint of solar collectors, of the large-scale deployment of solar collectors. So, for example, almost any type of material that you can even imagine that you would be able to collect photons from the sun and turn it into energy always leaves what we call an edge in the reflectance. In the ultraviolet, if you were to scan the ultraviolet, you would see that the ultraviolet has very low reflectance, and then all of a sudden, boom, it bumps up at particular wavelengths. And that's what this figure here is showing. All of these edges here are calculated spectra. So that's a really interesting way. And you might expect that you would have planets that, you know, in the future, we might cover a big chunk of the moon with solar panels in order to generate power. So this is a nice example of a technosignature. And here's one that we worked in. This is a paper we just put out. Atmospheric quote unquote pollutants, just meaning, you know, stuff in an atmosphere that would never be there naturally. And it may not be pollutants, it may be you're putting it there purposely for some reason. So here was a paper that we just recently did where we looked at the case of chlorofluorocarbons. These are the stuff that goes in. This was the stuff that actually, you know, was destroying the ozone layer, so it was bad for us. But you know, it's in the atmosphere, and what we did is we ran some computer models of planets where we put in one time, if you look over here, 1 times, 10 times, 100 times the amount of chlorofluorocarbons that are in the atmosphere now in the Earth. And we look to see how the climate would change because of that, because chlorofluorocarbons are a very powerful greenhouse gas. And then we made synthetic spectra. You know, this is the kind of thing that a telescope, the James Webb telescope, would see if it looked at. And we wanted to see whether or not you could see the chlorofluorocarbons. And actually, it turns out that the black, red, and blue lines here really show you that, wow, you would really see the chlorofluorocarbon, the absorption lines would be very, very visible. So even with JWST, if somebody were willing to give us 100 hours of JWST time and the planet 10 light years away had CFCs in their atmosphere, we would be able to find them. And that's a major milestone. What we showed with this paper was that Earth levels of a atmospheric pollutant would be visible with Earth levels of technology. So we could use technology we have now, the JWST, and see a planet 10 light years away that had the levels of an atmospheric pollutant that Earth has right now. So that was, you know, that showed us that we're getting to the point where really we can do technosignature science. Okay, so I'll just have a few more slides here. And let's just go back to the Fermi paradox. I wanted to touch on this again. And remember I said that there's the indirect Fermi paradox that people talk about, the great silence. And it's the idea that like, oh, you know, every night astronomers are looking, you know, they go out and they look for signatures of alien life in the universe. And nothing could be further from the truth. There's never been any money to do SETI. So there's this great paper that was done a few years ago where somebody actually went through, Jason Wright and his team went through and they looked at all the SETI searches that had ever been done, and they looked at what we call the parameter space. All, you know, it's how many stars have they looked at, what radio frequencies were they looking at, and if you imagine that the entire parameter space that you have to do a SETI search on, so again, that's number of stars, what frequencies are you looking at, how often are you looking, do you look just once, or should you look every hour, should you look every day, et cetera, et cetera. And they asked, okay, you know, if that's an ocean, we imagine that to be the Earth's ocean, how much of that ocean have we searched? And it turns out to be a hot tub. Basically, we've looked at 1 hot tub's worth of water. And so, you know, if you were to pull up a hot tub's worth of water from the ocean and you didn't find any fish, would you say like, well, that's it, there's no fish in the ocean? So, you know, that's what shows that there is no indirect Fermi paradox. We just haven't looked. Anybody who tells you that is just, you can say that I told them that they're wrong, okay? Another thing about the Fermi paradox that's interesting is what we, in my group, we ran computer simulations of a galaxy where we allowed ships. We simulated ships going from one star to the other, and we were trying to ask that question of, does the expansion wave stall? And so here is this, all the blue dots are stars in the Milky Way galaxy. The white dot is this one place that actually has a civilization, and I'm going to show you what happens over time as the galaxy rotates and ships are sent out, and when they turn white, they've been settled. So there you go. You see everything rotating. There it goes. There's the expansion wave. So you see pretty quickly on the timescale for the rotation of the galaxy, which is still, the galaxy rotates in about 200 million years. You have pretty much every star in the Milky Way will have been touched. So Sagan was wrong. Nothing. So this is the direct Fermi paradox. It's hard to get away from the direct Fermi paradox. So how do we get away from it? Well, one possibility, here's another simulation where we're just looking at a volume of space. These are all stars. The different colors here are different spaceships from different, or stars that have been settled by different seeds of civilization. And the important thing that we've done here, actually, let me stop this for a second, is, okay, so, the aliens, they start settling, they jump from one star system to another, they stop, they create a settlement, they build new ships, they go on to the next one. The settlement, their civilizations that they leave won't last forever, right? And so if you imagine that, yeah, civilizations come and go. So now what we're going to do is we're going to rerun that simulation in a small volume, and we're going to ask, and we're going to say, look, every civilization only lasts 10,000 years. What happens then? And so now that you can watch. So what you see here, there are constantly new settlements being born, and then there are other settlements that die, right? And the thing you notice here is, because the settlements are being born and die, they don't last forever, there are pockets of space here that are unsettled. Right. So there are regions where you have, alien civilizations, and there's other places where they're just, during the entire time of this simulation, there's no, there are these blue stars that haven't been. So let's run that again. You can just find some pockets here where there just hasn't been any aliens anytime soon. And that may be what we are. Once you actually ask about the steady state, what you find is that you can have pockets of space that just haven't been settled. So that may be an answer to the Fermi paradox. Okay, and I'll finally just note UFOs. So I did this, I do a lot of public writing. And so I did this for the New York Times a couple of years ago. I'm a physicist who searches for aliens. UFOs don't impress me. And what I meant by that was really, so there's, I think, the UFO stuff is interesting enough that somebody should study it. We should probably put some money into studying it. But the data just, okay, something's going on. There's lots of different explanations. And the idea that they're aliens, sorry, the data just does not support that. You've got a bunch of fuzzy pictures, and that's not enough to make the claim like, oh, we're being visited by, intelligent civilizations from across the galaxy. So I'll just sort of leave it there. So I'll leave it there, and I will say thank you.
Thank you so much for your talk, Professor. I believe Nakul has 2 questions for you. Nakul, take it away.
Hello, Professor. So here's my first question. Are human bodies capable of adapting to the environment of other planets, which could possibly support life?
Yeah, that's a great question. And probably not. Not without some, without being messed with. I mean, we'll have to see. Like certainly space is terrible for weightlessness, is terrible for the human body. But Mars, you have a picture of the Martian up here. Mars has about 1/3 the Earth gravity, and it does seem like 1/3 might actually, the body may be able to handle it. But it's possible that we're going to have to either do genetic engineering, or there's going to be a cocktail of drugs that you're going to have to take if you really are living on another world. So in general, there's Kim Stanley Robinson, who's one of my favorite science fiction writers. There's a story that he wrote where he really sort of focused on the idea that bodies are the fruits of their planets. That life and planets are closely tied together, and it may be that it's going to be hard for us to live on other planets, and we'll have to do things to ourselves in order to make that kind of adaptation.
That's amazing, and I agree with you. And here is my next question. Are there any other planets or astronomical bodies that could support life as we know in our solar system?
In our solar system, well, Yes, actually. I mean, in the possibilities, not probably our life, but we have the ocean moons of the gas giants. So Europa and Cetulus are two moons. One's a moon of Jupiter, one's a moon of Saturn, and they have deep oceans under, there's Europa in particular has a covering about 10 kilometers of ice with about 100 kilometers of water, liquid water below it. And, yeah, you could get life in there. We have life in the ocean. So if there's a deep sea vents, if you have hydrothermal vents, we think life on Earth started at the bottom of the ocean at hydrothermal vents. So if there are hydrothermal vents on Europa, you could have an ecosystem down there for sure.
And yeah, thank you so much, Professor, for answering my questions. And I'm giving over to Sergey, who also have some questions.
That was a wonderful presentation, Dr. Adam Frank. Thank
Sure.
you so much. Now I had two questions that are a bit more personal that I had while I was writing your introduction. My first question was, what was your favorite cover of the pulp science fiction magazines?
Yeah, this is great because these are kind of what these, and it was Amazing Stories in particular. That was one of my dad's favorite magazines. The one that really made an impression on me didn't have any aliens in it. It had guys in spacesuits like you see there on the one on the right, and they were on a mountain. I think it must have been on the moon. It was on an airless planet, and so they were up high on a mountain, a jagged mountain, and they were looking down into a valley where all the spaceships and the moon base was. And I don't know, I just thought that was the coolest thing. And it wasn't, I'm not sure if it was the moon or it might have been like one of the moons of Jupiter. And so there was a big planet hanging in the sky. And I was 5 years old and that was like, I'm done. That's it. This is what I want to do. I want to study space. Space is the coolest thing ever. And so, yeah, I have a profound memory of that particular cover. There was another cover that freaked me out, which was, there was a rocket ship with, the rocket, the exhaust coming out of the back of the rocket. And there were a bunch of astronauts like out on doing a spacewalk. And one of them, his body had just been, had just fallen into the plume of exhaust. And, you sort of saw his legs on the outside. And then, so I remember as a kid, I was like, well, it's terrible. So those two covers made a big impression on me.
Interesting. My second question is, are there any other planets or astronomical, out of the books that you wrote, which one would you say is your favorite?
Yeah, so as I said, you're asking me to see which of my kids is my favorite. My first book was about science and religion, and it's a topic I'm very interested in, or science and human spirituality, because I'm not one of these scientists who's like, anybody who believes in, believes that there's something to a spiritual life or spiritual endeavor, they're stupid. I think, there's a place for the sacred in science, even, so that's what that was a book that was important to me in writing it. I learned a lot. The last book I wrote, The Light of the Stars, Alien Worlds and the Fate of the Earth, was important to me because it's an idea that I've been very involved in climate change education and did some climate change research as well. And that book, I was really looking at climate change in the astrobiological context. And in some sense, what I was asking was, if there are other civilizations, do they all trigger climate change? Should we sort of see climate change as being something you got to get through? It's like adolescence. So I enjoyed that book. So yeah, I think probably, those two, if I had to pick.
Thank you very much. Now Maheen will ask her question.
First of all, I'd like to say thank you for coming on tonight. I thoroughly enjoyed the talk. So my question is, what does the ongoing search for alien life in the universe hold for the growth of astronomy in the future? So like, what doors, if any, will it open for us in general?
Yeah, well, what's interesting is, when I was a graduate student back in the late 80s, early 90s, what were considered to be the hot topics were things like cosmology and galaxy formation, looking way, way back to the beginning of the universe. And now I would say the hot topic is life. Astrobiology is the hottest field in astronomy, I would argue. Maybe that and gravity waves. And so, the possibility, this is, like I said, this is the oldest, I think it's the most important question you can ask. I think it's, whether or not we are alone in the universe is the most important scientific question that's out there. Because it's not just, whether there's civilizations. It would be great to find civilizations, but finding any life would transform our understanding of ourselves, because life is so different from non-life, right? Life is made of matter, made of chemicals and uses energy just like a star or a planet, but it's clearly very different. It's the possibilities for creativity and originality, and it's just, wow, what's going on with that? So if we're an accident, that's really weird. If we're not an accident, that's even weirder. That means that life is, the universe is full of this thing called life, which, who knows, allow it to evolve for billions of years, and it could spread through the galaxy and do who knows, because it's so powerful. So yeah, I think that's what will come from it.
That's a very interesting perspective. Thank you for that. I think Dorsa has a few questions as well.
Yes, thank you so much for your awesome presentation, Dr. Frank. This might be more of a general question, actually, but how did you come about in choosing this topic for your research in this presentation? Or in other words, what motivated you to search for life in the universe?
Well, it's actually, because when I started when I was 5 years old, right, that was the thing you're always interested in if you start with astronomy is like, whoa, life. It's just such a basic question. But I spent most of my career doing other things. I studied, most of my career has been studying things like star formation, or I've done a lot of work on the death of stars. So I have come to astrobiology later in my career. I probably started about 10 years ago. And the reason was because it's so cool, right? I'd spent a lot of time. I know a lot about, how a star like the sun's going to die. That was cool. But I wanted, there were other questions. I'm interested in a lot of different questions. And the question about because it was possible, I didn't get involved in it when I was, 40 years old, because there wasn't much to do with it then. But then they discovered planets and everything changed. And I just, I'm not going to sit on the sidelines and not, have some fun with this incredible question.
Yes, that's amazing. I probably would the same thing if I were you. I would switch to astrobiology for this very reason, to be honest.
Yeah, right. Yeah. It's an ongoing, it's a real thing now,
Exactly. So my second question for you is related to the characteristics that basically play a role in finding life through research. So how crucial and significant are finding biosignatures, and specifically an atmosphere on an exoplanet, in order to label that planet as a host for life?
Yeah, I mean, right now it's all atmospheres. That's the only way we have to look. We have to do atmosphere. What I described is what I was describing with biosignatures is what's called atmospheric characterization. And it's the only game in town right now. Now, later on in another 20, 30, 40, we may have invented other ways. If we could directly image a exoplanet surface, which is going to be hard, that would give us another way. But right now it's really sniffing, so to speak, the atmosphere using photons that have passed through it is the only way we can do it right now.
Great. Thank you so much for your time. We really, really appreciate it. Sure. I'm going to give it away to Nakul. Nakul, take it away.
Yeah, let me just check whether there is any comments in the YouTube channel. I guess no. So the questions are, that's it for today. And well, everyone, you have been listening to the AICO's Observatory Weekly TeleTube podcast, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of your university. The hosts this evening have been Dorsa, Sergiy, Maheen, and myself, Nakul. Thank you, Professor Adam Frank, for joining us this evening, and we had a great talk today. Make sure to leave any comments or questions in the comment section of the video and talk to us in the chat right now. We will be around for the next 20 minutes to answer your questions. All of our programs are free, but if you would like to make a donation, see our website at observatory.info.yorku.ca. You can always connect with us on Twitter with the handle York Observatory, and check out our website for show notes, contents update, and contact info at observatory.info.yorku.ca. You can also connect with our Instagram, which is Yorku Observatory. Thanks for tuning in. Clear skies and have a good night.